Planet 9 is still missing. No observatory has confirmed the planet's body or tracked the planet's motion. On June 30th of 2026, the search, with perhaps the greatest power to settle its case, officially began. Vera Rubin Observatory started its 10-year legacy survey of space and time from Cerro Pachón in Chile. It will sweep the southern sky every few nights and return to each field about 800 times across the decade. That repeated coverage can expose faint bodies by their slow motion and greatly enlarge the sample of frozen worlds beyond Neptune. It could reveal the planet itself if the object crosses sky that Rubin covers at a brightness Rubin can reach. Even without that direct detection, it can decide whether the orbital pattern behind Planet 9 grows stronger or falls apart. Extraordinary timing placed the new search beside a pattern already under pressure. In a preprint released in April of 2026, Amir Siraj, Christopher Chiba, and Scott Tremaine applied a statistical method designed to be insensitive to the uneven patches of sky covered by different surveys. They also enlarged the relevant stable sample from 21 objects to 25. With those additions, the reported significance of the orbital clustering fell from 2.7 sigma to 1.9 sigma. Its preferred direction became poorly constrained. Planet 9 survived that result as a viable hypothesis under heavier pressure. Once presented as an unusually coherent arrangement, the signal now looks less secure as the census grows. Yet the reason a giant unseen world was proposed has not become trivial. Several bodies beyond Neptune still occupy orbits so extreme that the known planets provide an incomplete explanation for their full pattern. Some analyses continue to find a meaningful alignment after estimating where telescopes could have found these bodies. Others find that the same detections fit an unclustered population. Inside that disagreement, the missing planet survives. Far beyond Neptune, the Sun holds a sparse population of frozen bodies on immense elliptical paths. Some return close enough to the planetary region for Neptune to scatter them repeatedly. Others keep their closest approaches so far away that Neptune can no longer reach them with a strong encounter. Sedna is the most famous example. Even at perihelion, the closest part of its orbit, Sedna stays more than twice as far from the Sun as Neptune. Something lifted that orbit away from the familiar giant planets. A passing star in the Sun's birth cluster could have done it long ago. A distant planet could also contribute. Sedna by itself cannot choose between those histories. Stronger provocation came from the orientation of several distant orbits together. An elongated orbit has a direction. One end carries the body's closest approach to the Sun. The opposite end reaches into the remote dark of aphelion. It also has a plane, which can lean relative to the broad plane occupied by the known planets. If a collection of distant bodies had been stirred without a continuing organizer, their long axes and orbital planes would be expected to spread around the Sun. Jupiter, Saturn, Uranus, and Neptune slowly twist those orientations at different rates. Over the age of the solar system, that differential precession should scramble an unsupported alignment. Against that expected scrambling, the early sample appeared to hold together. That resistance has a precise dynamical meaning. Without an extra organizing force, the direction of perihelion for each distant body should circulate through a full turn. One ellipse may rotate slowly, while another rotates faster because its size and eccentricity differ. Any temporary gathering should stretch, shear, and eventually disperse. Under continuing perturbation, circulation can give way to libration. An orbit's long axis then rocks around a preferred orientation instead of wandering through every direction. Some of the most remote bodies, therefore, seem to occupy such a protected region of orbital behavior. In 2016, Konstantin Batygin and Michael Brown examined the best characterized distant Kuiper belt orbits then available. Once bodies still strongly disturbed by Neptune were removed, 6 especially remote objects formed a striking arrangement. Their perihelia occupied a limited sector of the sky. Their orbital poles, the directions perpendicular to their orbital planes, also gathered together. Viewed as paths around the Sun, the ellipses shared a broad physical orientation instead of fanning out in every direction. Batygin and Brown estimated that a grouping at least that tight in both perihelion position and orbital pole would occur by chance only about 7 times in 100,000 under their statistical assumptions. Only 6 objects supported the estimate. It also depended on treating the discovery bias of those 6 as similar to the bias seen in a much larger collection of less extreme bodies. Openly, the paper noted that different surveys with poorly calibrated selection effects had assembled the complete catalog. Even with that weakness, the geometry demanded an attempt at a physical cause. An alignment left alone would precess a part. With too little present mass, the Kuiper belt cannot hold those remote orbits together efficiently through its own gravity. Past stellar encounters could raise perihelia, especially during the Sun's crowded youth, but a single ancient passage would struggle to maintain a common orientation against billions of years of later precession. Torque from a bound, massive body offered another route. Such a body would inhabit an orbit vastly larger than Neptune's. Its gravity would be weak during any single year, but it would keep acting for the entire life of the solar system. Repetition makes a distant perturbation consequential. Each remote Kuiper belt object circles the Sun again and again, while the unseen planet exerts a slight pull whose direction changes in a structured way. Certain orbital orientations survive that repeated forcing. Others wander into configurations where Neptune or the distant planet can destabilize them. Survivors can therefore carry the shape of a planet that has never been seen. Batygin and Brown found that an eccentric outer planet could confine the long axes of highly elongated Kuiper belt orbits. Stable, small bodies tended to place their perihelia on the side of the Sun opposite the proposed planet's perihelion. Their apsidal lines were anti-aligned. This arrangement sounds exposed because the enormous ellipses can overlap in a drawing. Long-term numerical integrations showed that overlap alone did not guarantee a collision or ejection. Resonant timing could keep the bodies from meeting at the dangerous parts of their paths. Their orbital periods could shift among high-order commensurabilities, while the anti-aligned geometry endured. Distance created a natural divide in the proposed planet's influence. Closer to Neptune, the combined pull of the known giants made orbital orientations circulate and mix. Farther out, Planet 9's influence gained leverage, and stable anti-aligned paths appeared. In the nominal 2016 calculations, apsidal confinement became visible beyond roughly 250 astronomical units, while the related grouping of orbital planes emerged farther out. This transition offered more than a visual match. Its location responded to the perturber's mass, perihelion, and orbital size, so future discoveries could force those properties into a narrower range. That same perturbation could move an object's perihelion. Bodies that once passed near Neptune could be lifted onto detached orbits, where close encounters ceased. In the simulations, that mechanism produced Sedna-like trajectories from a scattered population. It also generated objects on steeply tilted and even retrograde paths. Those outcomes mattered because highly inclined trans-Neptunian objects already existed and had resisted a simple origin within the usual flattened architecture. One planet could therefore connect several oddities. It could maintain the shared direction of the most distant stable ellipses. It could tilt their orbital planes into a related cluster. It could raise perihelia beyond Neptune's control. It could send a fraction of bodies onto extreme inclinations. None of those successes placed the planet in an image. They showed that a common perturber was dynamically capable of producing several features at once. In 2016, the paper offered a proof of concept. Precision was outside its reach. Its frequently repeated profile of Planet 9 came from an illustrative simulation. That nominal body had about 10 Earth masses, a semi-major axis near 700 astronomical units, an eccentricity near 0.6, and an orbital tilt near 30 degrees. 700 astronomical units described the semi-major axis and scale of that ellipse. With such eccentricity, the planet's distance would change enormously over one revolution. Useful parameter space remained broad. Long-lived anti-aligned configurations appeared in simulations with semi-major axes ranging roughly from 400 to 1500 astronomical units, and eccentricities from about 0.5 to 0.8. Brown and Battigan described the mass estimate as order of magnitude. Their inclined nominal experiment even suggested that a body somewhat more massive than 10 Earths might be needed to reproduce the nodal grouping at the observed distances. In a later summary of the early calculations, they described the 2016 data as consistent with masses between 5 and 20 Earths, semi-major axes between 380 and 980 astronomical units, and perihelia between 150 and 350 astronomical units. Those ranges defined families of possibilities rather than coordinates for a waiting telescope. Mass, orbital size, eccentricity, and inclination could trade against one another. Sometimes, a heavier planet farther away could sculpt a population resembling the work of a lighter planet on a closer orbit. With so few observed bodies, the calculation could not isolate one solution. Planet 9's position along any allowed orbit added another unknown. Predictive power gave the first dynamical case its deeper force. Far enough from Neptune, clustering should strengthen as Planet 9's slow torque gained control. Beyond the aligned group, a population with large perihelia should exist. Strongly inclined objects should connect dynamically to the extended scattered disk. New discoveries could sharpen the pattern, reveal the predicted populations, or dissolve the original arrangement. Over the following 5 years, searches added distant objects, and the models became more demanding. Only 6 bodies had supported the original claim. By August of 2021, Brown and Battigan selected 11 multi-opposition Kuiper belt objects for a new orbital analysis. Each had a semi-major axis between 150 and 1,000 astronomical units. Each kept perihelion beyond 42 astronomical units. A cut intended to remove bodies whose orbits diffuse strongly under Neptune. One object beyond 1,000 astronomical units was also excluded because it could have arrived from the inner Oort cloud and diluted the pattern. Multi-opposition observations were essential because a brief arc can leave the orbit of a remote body uncertain. Across one observing season, a distant object creeps through only a tiny sample of a revolution lasting thousands of years. Returning in later years tightens the estimate of its semi-major axis, eccentricity, and perihelion direction. For a detailed dynamical comparison, the 2021 sample favored bodies followed long enough to support stable orbital classifications. This chosen sample still showed clustering in the direction of perihelion and an orbital pole. Brown and Batygin updated their calculation of discovery bias and reported a clustering significance of 99.6%. That number expressed the result of their bias model and selection choices. Reading it as a 99.6% probability that Planet 9 exists would go beyond the calculation. Even genuine clustering could have another dynamical cause. After modeled observing preferences were applied, the calculation asked how comfortably the selected orbital angles fit a uniform underlying population. 5 years after the initial proposal, the new work tried to extract the hypothetical planet's properties from the shape of the distant population. It ran 121 large numerical experiments. Every experiment included the 4 known giant planets, a trial planet 9, and tens of thousands of test particles. From run to run, the trial planet changed in mass, orbital size, eccentricity, and inclination. Particles evolved under those gravitational fields and produced a synthetic distant Kuiper belt for each proposed planet. Different trial planets left different structures. Raising the planet's mass generally squeezed the perihelion cluster more tightly. Increasing its inclination pulled the orbital planes of the surviving objects toward a steeper shared plane until sufficiently large inclinations began to disrupt the clustering. Moving the planet's perihelion outward shifted the distance at which organized orbits emerged. Success required several features together, including the width of the observed cluster, its tilt, and the approximate transition between the more randomized inner population and the grouped outer one. For every simulation, the authors calculated how likely it was to produce the measured orbital angles of the real objects after discovery bias was included. Gaussian process software filled the gaps between discrete simulations. Markov chain Monte Carlo sampling then explored combinations of planetary parameters across that continuous likelihood surface. This turned the distant objects into an inverse gravitational problem. Many possible planets entered the calculation. Each one sculpted a synthetic outer solar system, and its survivors met the real sample. Support rose when a trial planet produced the right amount of alignment at the right distances and in the right orbital plane. It fell when the population became too narrow, too tilted, or organized too close to Neptune. No individual Kuiper belt object carried the solution. Combined orbital distributions supplied the constraint. By 2021, the inferred planet had become smaller and closer than the famous 2016 illustration. Under the paper's uniform prior, for orbital size, median mass reached about 6.2 Earth masses. Its central 68% interval ran from roughly 4.9 to 8.4 Earth masses. Median semi-major axis reached 380 astronomical units, with the corresponding interval extending from 300 to 520. Orbital inclination centered near 16 degrees, with an uncertainty of about 5 degrees. Perihelion centered near 300 astronomical units, with an interval from roughly 240 to 385. Inferred aphelion centered near 460 astronomical units. This was a radically different solar system citizen from the nominal body that dominated early artwork. It would still be a giant by mass, probably in the super-Earth or sub-Neptune range. Its orbit would remain far beyond every known planet. Yet its central estimate was no longer a 10 Earth mass world, averaging 700 astronomical units from the Sun. The data favored a body closer to 6 Earth masses on an ellipse whose central scale was a little under 400 astronomical units. Observed structure drove that change. Greater mass produced a narrower grouping than the real sample. Lower mass trials left a broader spread. But a lower mass planet had to sit closer to make the onset of clustering appear near the observed semi-major axes. Together, measured width and transition distance pulled the preferred mass and orbital size downward. Even this revised solution depended on assumptions made before the calculation touched the data. When Brown and Batygin used a prior, motivated by scattering a planet outward during the Sun's birth cluster, the median semi-major axis moved from about 380 to about 460 astronomical units. Angular orientation of the orbital path changed much less. Mass and eccentricity shifted with orbital size. Formation assumptions could therefore alter how far away and how faint Planet 9 was expected to be. Its present location also remained free. Long-term orbit averaged influence governs most of the distant Kuiper Belt's response to the perturber. Such influence can constrain the orientation and shape of the proposed orbit without revealing where the planet currently sits along it. Near aphelion, a body on such an orbit moves slowly and spends most of its time within the most distant arc. Some locations become more probable than others, but a long swath of sky and a large range of possible brightness survive. By 2021, the hypothesis had evolved from an illustrative 10 Earth mass perturber into a statistical estimate centered near 6 Earth masses. Planet 9 still had no detection. Its inferred properties were written into the distribution of smaller bodies, and that created the decisive vulnerability in the entire argument. Discovery never came from an even survey of the heavens. Their brightness falls with roughly the 4th power of their distance from the Sun. They must receive sunlight across the outward journey and reflect a tiny share back across the same distance. An extreme trans-Neptunian object may spend almost its entire orbit too faint for discovery, then enter reach for only a few decades around perihelion. Its discovery direction is therefore tied closely to the direction of its closest approach. Telescopes add another pattern. Each survey covers selected fields, reaches a particular limiting brightness, operates during certain seasons, and chooses which candidates deserve years of follow-up. Different designs carve different windows through the distant population. If several surveys search deeply in the same broad sectors, a population whose true orbital directions are uniform can produce a discovered sample that looks gathered. This problem was already visible in the 2016 paper. Its 6 key objects came from separate surveys, but separate surveys do not automatically create complementary sky coverage. Their detailed pointing histories and tracking efficiencies were unknown or unpublished. To estimate bias, the original chance calculation used other cataloged objects. That approximation became the exposed seam in the inference. In 2021, Kevin Napier and collaborators attacked that seam with 14 extreme trans-Neptunian objects from 3 programs whose observing behavior could be reconstructed. They used the Dark Energy Survey, the Outer Solar System Origin Survey, and the survey led by Scott Shepard and Chad Trujillo. For each program, they incorporated the published pointing history, limiting depth, and rules for tracking a candidate after discovery. Artificial populations passed through the actual survey footprints, and a simulator kept only the bodies each program could have detected and followed. Their selected sample was compatible with an underlying population whose perihelion directions and orbital poles were uniform. Depending on the statistic and assumptions, the joint probability lay between 17% and 94%. From this, the authors concluded that the well-characterized sample supplied no evidence for angular clustering. That conclusion stood beside Brown and Batigan's claim of 99.6% significance in the same year. Different samples and different methods for reconstructing discovery bias drove the disagreement. One analysis used a selected 11-object census with geometric biases estimated from the broader catalog. Napier's team trusted the smaller set from surveys whose selection functions could be simulated directly and found no need for clustering. By then, the missing planet had reached a more difficult kind of invisibility. Its proposed gravity appeared only after the search pattern of human telescopes was removed, and researchers disagreed about how that removal should be done. Before the distant orbits could accuse an unseen world, every patch of sky that was searched, missed, revisited, and abandoned had to enter the case. That is where the argument leaves orbital dynamics and enters the geometry of discovery. The catalog of distant objects records where telescopes looked, when they looked, how faint they could see, which moving sources survived follow-up, and which orbits happened to carry an object close enough to be noticed. Before any cluster can be treated as a message from a hidden planet, that machinery has to be separated from the pattern it may have created. The problem begins with the orbits themselves. The distant bodies at the center of the Planet 9 debate travel on extremely elongated paths. Most of the time, they are so far from the sun that reflected light makes them effectively invisible. They become easiest to find near perihelion, the closest point of the orbit to the sun. A discovery near perihelion, therefore, reveals more than a position on the sky. It also points toward the direction in which that orbit makes its closest solar approach. That direction is the very quantity that appeared to cluster in the original evidence. Now the telescope enters the selection process. A survey rarely covers the whole sky with equal depth. It may concentrate along the ecliptic, avoid the dense star fields of the Milky Way, lose some regions to weather, and return to other regions because their observing season is favorable. A moving object also needs repeat images before its orbit can be secured. A field that produced a candidate detection but no useful follow-up may contribute nothing to the final catalog. The result is a discovery footprint made of selected patches, depths, dates, and tracking decisions. If several surveys repeatedly inspect one family of sky directions, they will preferentially find distant objects near perihelion in those directions. When the resulting orbits are drawn from above, their long axes can seem to point together. Gravity may have arranged the alignment, or the surveys may have selected it. A uniform underlying population can acquire a non-uniform discovered sample after passing through a sufficiently uneven footprint. That possibility became central in the Outer Solar System Origins Survey, usually called OSOS. Its power came from characterization. The survey recorded where it pointed, how deep each field went, how efficiently moving objects were recovered, and whether discoveries were tracked well enough to avoid losing particular kinds of orbit. Those records allowed a synthetic population to be passed through a survey simulator. The simulator asked which imaginary objects would have entered the catalog if the imaginary sky had been observed in exactly the same way as the real one. In 2017, the OSOS team examined 8 large orbit objects found by the survey. Once the known selection effects were applied, those detections were compatible with an underlying population whose relevant orbital angles were uniform. The observed objects still occupied striking directions on a diagram. The simulator showed that a survey with the OSOS footprint could produce such a diagram without a distant planet arranging the intrinsic population. That result had a narrow but important meaning. 8 objects could not establish that every earlier alignment was an illusion. OSOS sampled a limited area and carried strong biases of its own. Its advantage was that those biases were measured. The study showed that its detections offered no independent requirement for clustering after the discovery process was reconstructed. It also demonstrated why a small collection from a cleanly documented survey could challenge a larger but less uniformly documented catalog. A broader test arrived in 2021. Kevin Napier and collaborators combined 14 extreme objects from the Dark Energy Survey, OSOS, and a survey led by Scott Shepard and Chad Trujillo. These surveys had published the information needed to model their pointing histories, depths, and tracking choices. The team calculated how likely the observed directions would be if the parent population were uniform, and the surveys then filtered that population through their actual selection functions. The results varied, with the angular quantity being tested, but the probabilities of consistency with uniformity ranged from 17% to 94%. In that defined sample, the mean longitude of perihelion and the orbital poles supplied no statistically persuasive clustering signal. The wording mattered. The paper reported no evidence for clustering in its sample. It did not turn 14 objects into proof that no physical clustering exists anywhere in the distant belt. Michael Brown and Konstantin Batygin reached a different result in the same year. Their analysis used a larger collection assembled from discoveries by multiple programs, including surveys whose full operating histories were not all available in the same characterized form. They developed an updated model of the directional biases attached to those detections, combined that model with numerical simulations of distant objects under Planet 9, and asked which planetary masses and orbits best reproduce the catalog. That treatment found that the clustering remained significant at 99.6% confidence. Conditional on the population model, the selection treatment, and the Planet 9 simulations, the preferred planet had a mass near 6 Earth masses and a semi-major axis near 380 astronomical units. The same analysis produced a map of where such a planet might appear. Those values were inferences from small bodies and simulated dynamics. They were not measurements of a planet seen in an image. The apparent contradiction between the characterized surveys and the Brown and Batygin result was not a dispute over a single calculation performed on identical inputs. The teams chose different objects, represented discovery bias in different ways, and asked related but distinct questions. The characterized survey approach accepted a smaller sample in exchange for explicit pointing and recovery records. The Brown and Batygin approach sought information from a broader heterogeneous catalog and constructed a model for the biases that catalog carried. This methodological split forms the fault line beneath the modern Planet 9 debate. If the broader bias model is accurate, the clustered catalog contains a dynamical signal that a distant planet can explain. If the documented survey samples are more representative, the apparent alignment may be an artifact amplified by small numbers. Each new object has unusual leverage because the sample is counted in tens rather than thousands. One orbit can strengthen a direction, another can pull directly away from it. In 2025, Amir Siraj, Christopher Chiba, and Scott Tremaine reopened the calculation with a different sample and a new set of dynamical tests. They first calculated which distant objects could remain stable long enough to preserve information about a slow gravitational sculptor. The resulting sample contained 21 stable objects, nearly twice the 11 used in the earlier Brown and Batygin clustering set. The team then examined how the angular pattern changed as the minimum semi-major axis moved outward. The strongest signal appeared among objects with semi-major axes beyond about 170 astronomical units. Their longitudes of perihelion clustered at roughly 2.7 standard deviations from a uniform null model. Other proposed patterns did not accompany it. The inclination, the argument of perihelion, and the longitude of the ascending node showed no comparable clustering. The surviving clue was therefore specific. It was an apparent preference in the direction of closest approach, not a complete geometric formation shared across every orbital angle. The team ran 300 simulations that included the known giant planets, a disk of test particles, and an additional planet whose mass and orbital elements varied. The best-fitting body had about 4.4 Earth masses, a semi-major axis near 290 astronomical units, an eccentricity near 0.29, and a low inclination near 7 degrees. That solution differed sharply from the Brown and Batygin reference population. Only about 0.06% of that older synthetic population fell within 1 standard deviation of the newer maximum likelihood region. This result briefly sharpened the mystery, while also moving the target. A clustering signal had returned in an expanded stability-selected sample, yet the planet inferred from it was smaller, closer, and less tilted than the widely circulated 2021 version. The analysis supported the possibility of an unseen perturber, but it also showed how strongly the predicted planet depended on which objects and statistical machinery defined the clue. Then 4 more objects entered the accounting. They were 2017 OF201, 2021 RR205, 2023 KQ14, better known as Ammonite, and 2024 FX26. The first and the third were especially awkward for a narrow apsidal cluster. Both were stable or sufficiently long-lived to qualify for the updated sample, and both pointed away from the preferred concentration. In April of 2026, Siraj, Chiba, and Tremaine introduced a conditional likelihood method designed to address the survey footprint problem from a new direction. The starting census contained 60 stable or metastable objects, with perihelia beyond 30 astronomical units and semi-major axes between 90 and 1,000 astronomical units. After the analysis, selected the distance range where clustering would be strongest, Beginning near a semi-major axis of 160 astronomical units, 25 objects remained in the final test. The idea behind the method can be understood through the geometry of one detected orbit. Once the location of an object, its distance, and the size and shape of its orbit are fixed, orbital motion permits two relevant solutions for the direction of perihelion. One places the object on the inbound side of the orbit. The other places it at the corresponding outbound position. Both solutions pass through the same observed place, at the same distance, with the same orbital size and shape. In a steady population, Keplerian motion gives those paired solutions equal intrinsic weight. An object moving inward through a given orbital location has a matching outward state governed by the same time weighting. The method therefore asks which member of each pair the catalog actually contains. If many detections repeatedly choose the member whose perihelion points toward one common direction, the pattern favors clustering. If the choices split as a uniform population predicts, the cluster weakens. At that fixed geometry, the uneven survey footprint is common to both solutions. The telescope looked at the same patch of sky and reached the same distance in either case. When the likelihood compares the two possible perihelion directions, that common footprint factor cancels. Repeating the comparison across the sample allows the analysis to estimate whether perihelion directions prefer a cluster without reconstructing every field from every contributing survey. The full version extends the comparison into 3 dimensions and uses the direction of the eccentricity vector rather than a flat orbital diagram. Tests on simulated surveys showed why the strategy is attractive. An artificial telescope could stare at 2 uneven fields and badly distort the raw angular distribution. The conditional likelihood still recovered the intrinsic clustering imposed on the simulated population because the shared pointing bias disappeared within each paired comparison. The cancellation has boundaries. The population model assumes that the directional distribution can be separated from the part describing orbital size and shape for this detached distance sample. Resonant populations can violate that simplification. The method also assumes that, after geometry is fixed, a survey has the same residual efficiency for the inbound and outbound solutions. A strong dependence on the sign of radial motion or another solution-specific selection effect would survive the cancellation. Detailed survey simulators remain necessary as a complementary check. Within those assumptions, the updated result was blunt. The 3-dimensional clustering significance fell from 2.7 standard deviations to 1.9. Simpler versions of the test gave still lower values near 1.6 and 1.7. The preferred direction became poorly constrained, spanning roughly half the sky. Search maps derived from the earlier, tighter orbital cluster were therefore narrower than the current sample justified. The fall was driven mostly by 2017 OF201 and Ammonite, 2021 RR205, and 2024 FX26. Change the result only slightly. In the full 3-dimensional calculation, roughly 1/4 of the loss in log likelihood came directly from each major outlier. The remaining half appeared when the best-fitting cluster was shifted to accommodate them, and consequently fit the other 23 objects less well. The change did not arise because older orbital measurements were revised into a different pattern. New qualifying bodies entered the sample and carried new directional information. That is exactly what a fragile small sample should do, when the visible catalog begins to widen. If a real shepherding mechanism creates a strong common direction, additional stable objects should eventually reinforce it. If the original pattern was partly a footprint and partly chance, additions should erode it toward uniformity. At one point, 9 standard deviations, the apsidal pattern is suggestive at most. Random uniform populations produce fluctuations, at least that strong, often enough to prevent a confident claim. The direction is also too broad to serve as the sharp celestial address once advertised. The original clue has not vanished, but its current form cannot carry the Planet 9 case by itself. That weakening might appear to leave the hypothesis with nowhere to stand. Yet a different test, published in 2024, points in the opposite direction. Instead of asking whether detached, distant orbits share an apsidal direction, Batygin, Alessandro Morbidelli, Brown, and David Nesvorny studied long-period objects that remain near the plane of the solar system and cross inside the orbit of Neptune. These bodies probe a different dynamical question. Neptune normally acts as a barrier. Objects scattered by Neptune can wander in orbital energy, but driving the perihelion steadily through the planetary region is difficult in a model where Neptune, the galactic tide, and passing stars do all the work. A distant massive planet can slowly modulate eccentricity and inclination. That secular forcing can lower perihelia and feed objects across the Neptune barrier, while some remain on relatively low inclination paths. The study began with 29 catalogued objects satisfying broad orbital cuts. It retained 17 whose paths had been established across multiple oppositions. Each had a semi-major axis beyond 100 astronomical units, a perihelion inside 30 astronomical units, and an inclination below 40 degrees. The observed perihelia formed a comparatively flat spread below the orbit of Neptune, rather than piling tightly against the boundary. 2 long integrations supplied the comparison. One included a planet of 5 Earth masses on an orbit with a semi-major axis of 500 astronomical units, eccentricity of 0.25, and inclination of 20 degrees. The other omitted that planet. Both incorporated the known giant planets, the galactic tide, stellar passages, early giant planet migration, and an early stellar cluster environment. The experiment was therefore a comparison between 2 detailed histories, but only one chosen version of Planet 9 represented the entire planet family. In the simulation, with no added planet, the number of objects dropped rapidly as perihelion moved inward from Neptune. In the simulation with Planet 9, secular forcing repeatedly pushed detached objects into Neptune crossing states and produced a much flatter perihelion distribution. That flat simulated shape resembled the 17 observed bodies. The resemblance survived the bias correction used by the authors. That correction conditioned the comparison on the distance at which each real object was discovered. For a detection at a particular distance, the method treated the object as a probe of the simulated perihelion distribution interior to that distance, then corrected for the unequal time that different orbits spend in the detectable region. The approach reduces the effect of object brightness and varying survey depth. It assumes that the orbital distribution is independent of object size and treats longitude-dependent footprint effects as secondary. Using a Kolmogorov-Smirnov test, the Planet 9 model produced a probability near 0.41, consistent with the data under that comparison. The model without Planet 9 produced a probability near 0.0034. The team then built a separate statistic from the transformed positions of all 17 objects. The value for the planet-free simulation landed roughly 5 standard deviations from the distribution expected when those transformed values are uniform. That roughly 5 sigma phrase is easy to turn into the wrong story. It was not the significance of a detected planet. No planetary light, position, orbit, mass, or gravitational acceleration was measured. The number described how poorly one specific planet-free simulation reproduced one bias-corrected distribution of 17 selected Neptune crossers, according to a statistic built for that comparison. The alternative was one fixed Planet 9 simulation, not an exhaustive contest among every possible history of the outer solar system. The authors themselves described the current data comparison as inherently imperfect. The discoveries came from multiple surveys, and the bias treatment could not reproduce every pointing and tracking decision. The assumed independence between object size and orbit may fail. The selected planet parameters were not varied across a broad posterior in this test. Those limitations weaken any attempt to call the result a discovery, but they do not erase the physical contrast that generated it. The contrast also makes predictions. In the simulations, the ratio of low-inclination Neptune crossing objects to comparable bodies with perihelia beyond Neptune was about 3% with Planet 9 and about 0.5% without it. The crossing phase lasts only around 100 million years, short compared with the age of the solar system. A continuing source must therefore replenish the population. A large and uniformly selected survey can count that flow instead of reconstructing it from 17 historical discoveries. The two evidence lines now pull in opposite directions. The famous apsidal alignment among detached objects has weakened to 1.9 standard deviations, as the stability selected sample grew from 21 to 25. The low-inclination Neptune crossers still resemble the output of a particular Planet 9 simulation far more than the chosen planet-free model. One clue is an angular pattern vulnerable to sky footprints. The other is a perihelion distribution vulnerable to population modeling, discovery distance assumptions, and the narrow choice of simulations. Neither result can simply cancel the other. They involve different objects, different orbital behavior, different selection corrections, and different null hypotheses. A future census could make the apsidal directions more uniform, while confirming an unexpected supply of Neptune crossers. It could reinforce both patterns. It could dissolve both. The present tension means that Planet 9 has lost the clean statistical foundation that once made its orbit appear predictable, yet the outer solar system still contains a dynamical feature that a distant planet can naturally produce. That tension leaves a harder question than the original alignment diagram. If the planet is real, its gravity has allegedly written more than one signature into the distant belt. If the planet is absent, small samples, survey geometry, and incomplete models have combined to imitate those signatures with remarkable persistence. Either way, inference has reached the limit of what a few dozen remote bodies can securely reveal. The obvious escape is to stop inferring and find the source. Major optical and infrared surveys have already searched enormous regions, injected synthetic planets into their data, and ruled out much of the once favored parameter space. Yet no moving world has emerged. Why has a planet massive enough to reshape distant orbits remained invisible? And where can it still hide after years of direct searches? Planet 9 could be massive enough to reshape the distant solar system and still be almost impossibly faint. That sounds like a contradiction, only while distance is treated as empty space. At the edge of this search, distance is an active disguise. It weakens the light, slows the apparent motion, enlarges the uncertainty in position, and places the suspected planet against some of the most crowded fields in the sky. Konstantin Batygin and Michael Brown inferred an orbit that offers no single point where a telescope can simply look. Their model describes a family of possible orbits, each carrying its own range of masses, distances, orientations, and present locations. Distant objects constrain the shape and direction of that orbit more strongly than they constrain where the planet must be today. Its place along the path remains one of the great uncertainties. Such a world can therefore be permitted by the dynamical evidence, while hiding across a long arc of sky. Near the far end of that arc lies both the most difficult search region and a natural place to find an eccentric planet. There, the world would move most slowly and spend the greatest amount of time. That makes it statistically easier to catch there in time, but physically harder to recognize. It is farther from the sun, fainter in reflected light, and slower against the background stars. That orbital geometry raises the chance of its presence while lowering the strength of its signature. Surveys can stare into the correct region and still lack enough depth or enough visits to connect the detections across months and years. Even inside that arc, brightness is unforgiving. Optical telescopes usually cannot rely on the planet glowing. They receive sunlight reflected from the planet. Sunlight first spreads outward from the sun. By the time it reaches a world hundreds of astronomical units away, its intensity has already fallen with the square of the distance. Planet 9 would reflect only part of that weakened light. From there, the reflection spreads across space on its way back toward Earth, losing intensity with the square of the distance again. Those two losses multiply. Reflected light from a distant planet, therefore, fades approximately with the fourth power of its distance from the sun. If the same object is moved twice as far away, it does not become merely 4 times fainter. It becomes about 16 times fainter. Move it 3 times as far away, and it becomes about 81 times fainter. Even a modest change in the unknown distance can push a plausible survey target below the detection threshold. Here lies the first secret of the search. Planet 9 needs no cloak. Geometry supplies one. Several Earth masses can hide because the light used to reveal the world has been weakened twice. Infrared observations offer another way to look. Far from the sun, a giant planet may retain heat from its formation and slow contraction. That thermal emission does not have to travel from the sun to the planet before it can be detected. It begins at the planet and spreads outward once. Its apparent thermal brightness therefore falls approximately with the square of the distance, not the fourth power. That difference is enormous. In reflected light, doubling the distance imposes a factor of 16. In thermal emission, the same change imposes a factor of 4. Infrared searches are not automatically easy. Cold conditions push the strongest emission toward far infrared wavelengths, where the sky contains dust, cirrus, galaxies, detector artifacts, and sources blended by limited resolution. But the distance penalty is fundamentally less severe. Nearly erased from visible images, the world may still leave a measurable trace of heat. If the solar system feels larger now, subscribing is a small way to help cosmic drift keep following the evidence beyond Neptune. Optical searches held a different advantage. Their cameras had already watched enormous areas of sky for other reasons. Every archived exposure offered another chance that Planet 9 had crossed the detector without being recognized. Finding an unresolved source was only the start. Researchers had to link detections across different nights while Earth moved. The planet moved, weather changed, image quality shifted, and countless stars and galaxies remained fixed behind it. The Zwicky Transient Facility supplied one of the first broad tests of the modern prediction. Its public archive covered most of the expected path, visible from the north, apart from the southernmost region and the densest fields around the center of the galaxy. The search looked for combinations of transient detections that could belong to one slow-moving body following a physically allowed orbit around the Sun. No Planet 9 appeared. Under the reference population derived from the Brown and Batygin orbital model, the Zwicky search was sensitive to about 56% of the predicted possibilities. That was a large exclusion, but it was not an even sweep of all imaginable Planet 9s. It depended on the assumed distribution of mass, orbit, brightness, and position. A darker planet, a more distant planet, or a planet outside the model-favored region could survive. The Dark Energy Survey tested a different piece of the sky. Its 6 years of deep southern imaging had already produced a large catalog of objects beyond Neptune. Researchers inserted 100,000 synthetic Planet 9s into a detailed simulation of the survey. Each artificial world was drawn from the dynamical probability model and given a predicted apparent brightness. The exercise asked a direct question. If a planet from that model had been present in the Dark Energy Survey footprint, how often would the actual observing pattern have recovered it? Again, no planet was found. The southern footprint by itself excluded about 10% of the reference population. Much of that region overlapped possibilities already tested by the Zwicky search, so the genuinely new exclusion was about 5%. Together, the two surveys removed a little more than 61% of the modeled parameter space. The numbers could sound like odds against the planet, but they were not. 61% excluded did not mean a 61% probability that Planet 9 was absent. It meant that 61% of a particular synthetic population would probably have been detected and had not been. The result squeezed the model. It did not assign a simple chance that the world existed. Pan-STARRS 1 then brought a much broader northern archive into the search. Between 2009 and 2015, the survey repeatedly imaged most of the sky north of a declination near -30 degrees. Its camera was deep enough to reach much of the expected brightness range. Its weakness was cadence. Many fields had only a modest number of useful visits, and a remote planet might appear in only a handful of them. The search began with roughly 1,260,000,000 transient detections. Most were not distant worlds. They were image defects, cosmic rays, variable sources, diffraction features, subtraction failures, or real stationary objects that had appeared inconsistent because the observing conditions changed. The computational problem was to find tiny groups of detections whose positions could be explained by the parallax and orbital motion of one body at the edge of the solar system. That requirement is what separates a moving object search from a catalog search. One detection cannot define motion. Two detections can be paired in an enormous number of accidental ways. A longer chain begins to demand a coherent trajectory. In the pan-stars analysis, candidate linkages had to contain enough detections to support a Keplerian orbit and survive visual inspection. Known distant objects reappeared, demonstrating that the machinery could recover real bodies. Planet 9 did not. When the Zwicky Transient Facility, the Dark Energy Survey, and this pan-stars search were combined, they excluded 78% of the Brown and Batygin 2021 reference population. That was the sharpest optical constraint yet. Almost 4/5 of the locations and brightnesses favored by that particular model had been searched deeply enough that the planet should have appeared. The remaining fifth was not distributed randomly. The null results pushed the likely present location toward harder territory. Much of the surviving probability gathered near the northern galactic plane, where the proposed planet could be close to the slow, distant part of its orbit, and therefore especially faint. A smaller surviving region lay near the southern galactic plane and beyond the southern boundary of the northern surveys. The galactic plane is not a wall in space. It is a wall of information. Looking through it means looking through the crowded disk of the Milky Way. Stars overlap. Dust changes the background. Variable sources generate false transients. Bright stars create halos and diffraction patterns. Tiny imperfections multiply because every exposure contains so many sources. A slow point moving across that background can be real and still fail to form a clean chain. This produced an uncomfortable inversion. Each successful null result made the remaining search smaller, but it also made the surviving region more difficult. The easy sky was being removed first. Planet 9, if it matched the model, was being cornered into the places where surveys were least complete. A second pan-stars analysis, reported in 2025, widened the question. Instead of tuning the search only to one narrow family of Planet 9 predictions, it tested sensitivity to distant planets across a broad range of distances and apparent motions. Synthetic objects were inserted in many directions, so the recovery efficiency could be measured without assuming that every distant world had to resemble the preferred Planet 9 orbit. The search recovered 692 solar system objects. 642 were objects beyond Neptune. 23 were recognized dwarf planets, and 109 objects were not yet listed by the Minor Planet Center when the catalog was compared. These recoveries showed that the search could find faint, slow bodies in the real pan-stars data. Yet it found no Planet 9 and no other planetary object. The result concentrated the remaining Planet 9 parameter space even more strongly toward the galactic plane. That phrase matters. Concentrated did not mean occupied. The survey had identified where its sensitivity weakened and where the model could still survive. The remaining region was a prediction filtered through selection effects, not a glowing mark left by the planet. Optical astronomy had therefore reached a strange frontier. The archives contained enough information to rule out most of the favored solutions, but the surviving solutions were protected by the same stellar crowding that made the Milky Way beautiful. The search needed a second kind of evidence, one that treated heat rather than reflected sunlight as the signal. 2 studies turned to old far-infrared maps of the entire sky. Their results sounded similar enough to be easily confused, but they were distinct searches with distinct candidate sets. The first compared observations from Iris in 1983 with observations from Akari more than 2 decades later. A distant planet would have shifted between the 2 epochs. It could appear as an infrared source at one position in the older survey and at another position in the newer survey, while ordinary stars and galaxies would remain fixed. The researchers searched for plausible Eras and Akari pairs consistent with a body hundreds of astronomical units away. After catalog filters and motion tests, 13 pairs remained. Direct inspection of the infrared images reduced them to one good candidate pair. The older source was absent from the later image at its original location. The newer source was absent from the older image at its later location. Their separation was compatible with the broad motion expected over the 23-year interval. That is intriguing, but it is not a detection of Planet 9. The pair contains one useful position from Iris and one from Akari. 2 positions can suggest motion, yet they cannot show a unique orbit. Different combinations of distance, direction, temperature, source confusion, and measurement error can imitate the same pairing. The source must be recovered again before the line between those old points becomes a physical path. The second study used Akari alone and a different time signature. Akari scanned the same region more than once within a day, then returned months later. A planet several hundred astronomical units away would move very little over a few hours, allowing repeat detections close together. Over roughly half a year, Earth would move to the other side of its orbit, and the apparent position of the planet would shift through parallax. A stationary infrared source should remain in place. A remote solar system body should not. After removing known catalog sources, bright backgrounds, infrared cirrus, and suspicious single-scan events, the study retained 2 possible candidates. Each appeared twice within about 1 day and was absent at the same location about 6 months later. Their positions and far infrared brightnesses fell within ranges considered plausible for Planet 9. Those 2 Akari candidates were not reported as matches to the single Eris and Akari pair. They arose from a separate search using a separate method. There is no basis for combining them into one object, treating them as overlapping evidence, or counting them as 3 sightings of the same planet. They are 3 candidate outcomes from 2 different analyses, each limited by sparse observations. The word candidate carries the entire burden here. Far infrared maps are difficult. Galactic dust can form compact knots. A passing asteroid can enter a scan. A detector can register a cosmic ray. A real variable source can appear in one epoch and fade in another. Limited angular resolution can blend several objects into one apparent source. Careful filtering reduces these possibilities, but only repeated motion can distinguish a planet from every convincing imitation. A real Planet 9 would have to return where its proposed motion says it should. New observations would need to show a consistent direction and speed. The annual parallax caused by Earth would need to fit the same distance in every epoch. The slower curvature from the planet orbiting the Sun would need to agree with a bound Keplerian orbit. Its brightness and color would need to remain compatible with one cold body, rather than with unrelated sources blended in the old infrared beams. More positions would progressively remove false solutions. One pan-stars analysis used at least 9 linked detections as a practical threshold for testing a distant orbit. The exact number depends on timing, precision, and geometry, but the principle is concrete. The observations must predict the next position before it is measured. A candidate becomes persuasive when a telescope points to that prediction and finds the same body moving onward. Recovery could also connect the visible and infrared searches. A cold object found in an old Akari beam might be sought with a modern optical telescope at its extrapolated position. An optical detection might then be checked against the far infrared source. The two measurements would constrain different properties. Reflected light depends strongly on size, surface reflectivity, and distance. Thermal emission depends on size, temperature, and distance. Together, they could narrow the physical identity of the world. Without an orbit, however, even a perfect-looking infrared source remains an address without a resident. This is where Vera C. Rubin Observatory changes the scale of the problem. Rubin began issuing its first scientific alerts in February of 2026. Each alert reports a source that has changed or moved relative to a reference image. The alert stream is not a list of discoveries. It is a rapid record of differences, sent within minutes, so software brokers and research teams can decide which changes deserve attention. On June 30th, 2026, Rubin officially began the Legacy Survey of Space and Time. The survey is designed to run for 10 years. On a productive night, the observatory can collect about 10 terabytes of images and issue as many as 7 million alerts. Over the full survey, a typical area of sky will be visited about 800 times. For Planet 9, repeated visits matter more than raw image count. One Rubin exposure might contain the planet as an unresolved detection among millions of sources. A second visit introduces motion. Later visits trace the combination of parallax and orbital drift. Hundreds of visits can turn a barely visible displacement into a trajectory that survives gaps, bad weather, and crowded backgrounds. Rubin also reaches deeply into the southern sky, including regions that older northern surveys could not cover. It can test surviving space near the southern galactic plane and below the pan-star's boundary. It cannot guarantee complete coverage of every remaining possibility. Some favored northern positions lie beyond its main footprint, and the faintest versions of Planet 9 may still challenge individual exposures. Crowding in the galactic plane does not disappear because the camera is newer, yet repeated deep imaging attacks the exact weaknesses that allowed a slow body to escape earlier archives. The direct test is easy to state. If Planet 9 crosses the Rubin footprint at detectable brightness, its positions should link into a distant bound orbit. The measured motion should then predict recovery in later Rubin images, and perhaps in older survey data. Continued non-detection, once the survey efficiency is measured, would eliminate still more combinations of position, brightness, and orbit. Rubin carries a second test that may be just as decisive. The Planet 9 argument began with the orbits of a small number of extremely distant objects. Their apparent clustering supplied the dynamical clue, but a small sample is vulnerable to where telescopes happen to look and what they were capable of finding. Rubin is expected to discover vast numbers of objects beyond Neptune with one repeatedly measured survey strategy. That enlarged orbital census can test the cause, even if the planet itself remains unseen. If the new distant orbits preserve the same directional clustering after Rubin selection effects are included, the case for a common sculpting influence becomes harder to dismiss. The expanded sample could sharpen estimates of the perturber orbit and move the predicted search region. If the clustering weakens as less favored parts of the sky are surveyed, the original evidence for the planet weakens with it. This creates two paths to an answer inside the same experiment. Rubin can search for the proposed world across repeated detections, while also testing whether the orbital pattern that predicted it survives a much larger census. A moving source without the expected dynamical influence would demand one explanation. A strong orbital pattern without a visible planet would demand another. A planet and its predicted pattern appearing together would close the loop. The timing could hardly be more charged. As the older surveys narrowed the hiding places and Rubin began to enlarge the census, new distant bodies reported in 2025 and 2026 started to press against the original clustering. Their orbits did not simply add more dots to the old pattern. They changed the shape of the argument that had made Planet 9 necessary. The search was no longer only closing in on a hidden world. It was about to discover whether the map leading to that world had been drawn from an incomplete sky. The next challenge did not arrive from a failed search for the planet. It arrived from an object that had already crossed years of old images without being recognized. Those images belonged to a survey built to study galaxies. Its camera had returned to parts of the sky at irregular times, leaving a scattered trail of exposures rather than a deliberate solar system search. When researchers connected detections made on different dates, the same body appeared at the predicted position again and again. The motion belonged to a real object. Its fitted orbit was extraordinary. The object is called 2017 OF-201. It is now about 90 astronomical units from the Sun. Its elongated path carries it inward to roughly 45 astronomical units and outward beyond 1600. One circuit takes about 24,000 years. That orbit creates a cruel discovery window. The object spends almost all of its time too far away to appear in the survey. Its discoverers estimated that it would be detectable for only about 0.5% of each circuit. Finding it was like opening a shutter during the brief fraction of an age when the body happened to be near enough. Its timing adds a remarkable historical coincidence. 2017, OF-201, last passed closest to the Sun. In 1930, the same year Pluto was discovered. Even at its brightest, it remained about 4 magnitudes fainter than Pluto. One distant world entered the known solar system, while another followed an immense path through the same era without being noticed. Brightness and an assumed reflectivity suggest that the new object is roughly 700 kilometers wide. That estimate could change when its surface properties are measured. Even so, it is probably large enough to be nearly round. Its existence also implies a much larger hidden population. If an object is visible for such a small fraction of its orbit, finding one nearby suggests that many related bodies spend their time far beyond the reach of present surveys. For Planet 9, the important feature is not the size, it is the direction of the orbit. 2017 OF-201 does not join the famous group of aligned perihelia. Its closest approach points well outside that apparent cluster. The object therefore enters the case as a contrary witness. A pattern that seemed tighter when the sample was smaller has gained a large and dynamically interesting exception. The Discovery team tested published versions of the hidden planet across many possible orbital phases. In the final analysis, those configurations ejected more than half of the simulated copies of the new object. The mean ejection times were roughly 1/4 to 1/3 of a billion years. Without the proposed planet, the orbit was far more durable under the known giant planets and the galactic tide. That result does not eliminate every possible Planet 9. The test used one mass and one orbit from a wider family of proposals. A planet farther away, less massive, differently tilted, or placed at another phase of its orbit could produce another outcome. The result still matters. Any viable hidden planet must preserve the difficult objects that actually exist, not only reproduce the ones that first inspired it. Another contrary witness arrived from a different search. 2023 KQ-14 carries the nickname Ammonite. Its perihelion lies about 66 astronomical units from the Sun. Its semi-major axis is about 252 astronomical units, and its orbit has remained stable in simulations spanning the age of the solar system. Neptune cannot easily reach it there. Ammonite also refuses to point with the older Sedna-like objects. Its orientation falls outside their alignment and fills a previously sparse region in perihelion distance. Simulations suggest that those bodies may once have shared a primordial clustering more than 4 billion years ago, before their directions spread apart. That possibility changes the question. A present planet is one way to maintain an orbital pattern. An early stellar encounter, a passing rogue planet, or the Sun's birth environment could instead create a pattern that later diffuses. The same frozen bodies can carry both a current gravitational signal and a fossil from the solar system's youth. Separating those histories requires more objects and better knowledge of how each one was selected. Ammonite does not simply vote against every hidden planet. Its stable orbit favors versions placed farther away, around 500 astronomical units, over closer massive versions. A discovery can weaken one proposed orbit while leaving another alive. Planet 9 is not one fixed prediction tied to one agreed coordinate. It is a changing range of masses and paths inferred from a changing population. Together, these two bodies did more than weaken the current clustering statistic. They forced any surviving hypothesis to explain contrary directions and long-term stability at the same time. That pressure opens a wider possibility. There may even be more than one hidden planet question. A 2025 measurement examined the mean plane of distant, non-resonant objects. Between about 80 and 400 astronomical units, the measured plane showed a tentative warp relative to the plane set by the known planets. If that warp is real, simulations favored an unseen body between roughly the mass of Mercury and the mass of Earth, orbiting around 100 to 200 astronomical units away. Such a body would not be the canonical Planet 9. It would be smaller and closer than the super-Earth proposed to shepherd the most distant perihelia. The measurement could still be spurious, and the present sample cannot resolve it. Its value lies in what it reveals about the task ahead. A larger census may not return one simple yes or no. It could expose a different planet, an unexpected distribution of small bodies, or the dynamical scar of an ancient event. The outer solar system has several mechanisms capable of moving an icy body into a strange orbit. Neptune can scatter an object outward. The galactic tide can change the perihelion of a body that travels far enough from the Sun. Passing stars can disturb the young solar system. A temporary rogue planet can scatter bodies before escaping. A surviving distant planet can continue shaping orbits for billions of years. Each mechanism leaves a different combination of directions, inclinations, perihelia, and stability. A sparse sample allows several histories to resemble one another. A large sample forces them apart. That is why the new survey can settle more than a search box on the sky. A direct discovery would require a source to move consistently across repeated observations. Its apparent shift would combine its own slow orbital motion with the changing viewpoint of Earth. Further measurements would have to connect those positions into a solar system orbit. Its brightness and color would need to fit a body at the inferred distance. Thermal observations could test whether its emitted heat agrees with the proposed size. Only that chain could turn a candidate into a planet. The population test is equally decisive. If thousands of new distant objects preserve a strong apsidal direction after their selection effects are measured, the gravitational case will strengthen. Their inclinations, detached perihelia, Neptune crossing paths, and orbital poles would then have to agree with one viable planet, rather than a succession of separately tuned versions. If the apparent patterns disperse as the census grows, the original inference will lose its foundation even if a few unusual orbits remain. The Vera C. Rubin Observatory can attempt both tests. Early optimization data yielded more than 11,000 asteroid discoveries, including hundreds of bodies beyond Neptune. Now, its repeated survey images can expose a slowly moving world and multiply the population used to test the old patterns. No discovery is guaranteed. A distant planet could be fainter than expected. Much of the surviving search region lies against the dense galactic plane, where crowded stars complicate moving object searches. The planet could occupy northern sky outside the main survey. It may not exist. Those limits make the possible outcomes more informative, not less. A confirmed moving planet would explain why several dynamical anomalies appeared together and would add a new class of world to the solar system, a super-Earth, on an orbit thousands of years long. Its mass and path would constrain how the giant planets migrated, and whether another planetary core was scattered outward early in solar system history. A strong population rejection would force a different reconstruction. Sedna, Ammonite, 2017, OF 201, and the low-inclination crossers would still need origins. The answer might lie in the Sun's birth cluster, stellar flybys, galactic tides, a lost rogue planet, or several mechanisms acting at different times. Removing Planet 9 would not restore a simple outer solar system. It would make that distant population the surviving evidence of events that no telescope witnessed. The present answer is therefore exact. Planet 9 has not been detected. Its classic apsidal clue has weakened to 1.9 sigma in the newest accepted analysis. Some other dynamical evidence remains supportive, but depends on population models. Optical surveys have eliminated large portions of leading predictions. Infrared searches have produced candidates that still lack confirming orbits. New distant bodies both constrain the planet and challenge the alignment that inspired it. The consequence is larger than the count of planets. The last confirmed giant does not mark the end of the Sun's dynamical reach, and the bodies beyond Neptune are not a quiet leftover ring. They exchange momentum with planets, respond to the galaxy, and preserve the violence of an early stellar neighborhood. Whether Planet 9 exists or not, its search is measuring that hidden architecture. For now, 8 planets are confirmed. Beyond Neptune, the experiment has finally become large enough to give the 9th a fair trial.